Section 2.5. So we are ending up this section. This is the end of the exponential unit. So this is our last new lesson. So section 5 talking about something very specific called half-life models. So in the last lesson we talked about exponential growth and decay. This is a very specific kind of decay. So we're looking for substances that decay exponentially to 1/2 of what they used to be. So for example, let's take the easy one here, NCAA basketball tournament. It starts out with 64 teams. Everybody plays a game. Then we're down to 32 teams. We play a game again. We're down to 16 teams. And then 8. And then the final 4, championship game, and we have one winner. So what you see here is 1/2 of 64, 1/2 of 32, 1/2 of 16. So every step of the way in this tournament, the number of teams still alive decreased by half. So that is a decay problem where everything decays by 1/2. A medicine or other substance in the body, a lot of times it's advertised you take this drug like aspirin, and how long until it's decreased till half the amount that it used to be. So that's called the half-life. How long it would take until whatever you ingested is in your bloodstream equal to half of what it started out to be. Radioactive substances, very common, nuclear waste, has a long half-life. It takes a long time for a nuclear waste to get down to half of what it used to be. So let's look at this specific case. So you recognize this, that is exponential decay. If I said, write an exponential model for something decaying by 50%, remember in the last unit, our lesson was y equal a 1 minus r to the x, where r is the rate, okay? So if you look at this particular rate right here, 0.5, that means 50%. So this is something that's decaying by 50%. Well, what is 1 minus 0.5? 1 minus 0.5 equals 0.5. So if I just substitute that in, this becomes my formula. Y is equal to a 0.5 to the x. That is representing something that decays by 1/2, okay? We're going to modify the formula just a little bit, so stay with me here. We're going to modify it to look like this. Y is equal to a 0.5 to the x over h. And the reason I'll do that is as follows. So you should be very familiar. Y, it hasn't changed. That is our future value of whatever we're modeling. A has not changed. That is our initial value. The variable x, our exponent in every problem we've had this unit, represents time. And then the new one here, h is equal to the half-life. So that is the amount of time it takes for whatever we're modeling to reach 1/2 of the quantity it started out with, okay? So let's do an example. And again, as always, you will be given the formulas, but you would not be given explanations as to how to use them. So our half-life formula, we just wrote it down there above, is y is equal to a 0.5 to the x divided by h. So uranium-235 was the primary isotope in the World War II bombs over Hiroshima and Nagasaki, Japan. Uranium-235 has a half-life of 703 million years. The bomb contained 2 pounds of uranium-35. Write an equation modeling the amount of decay in uranium to find your variables, okay? So I could just use this formula here, y equal a 0.5 to the x over h. Okay, so it says, what do we start at? We started out with 2 pounds. So a, that is my initial value of 2 pounds of uranium. And h is my half-life. And that is determined to be what? 703.5 million years. And that should be it, okay? So it says how much uranium would be left after 1 million years. So, and y, my future value, is going to be the amount of uranium in pounds, okay? If they ask me how much uranium is left after 1 million years, That's when we're saying X is equal to 1, okay, 1 million years. So my formula would be Y equal 2 pounds times 0.5 to the X, so that's 1 over 703.5. So that will tell me how much is left after 1 year. Okay, excuse me, 1 million years, because this was measured in millions of years. So let's do that calculation on our calculator. So I've got, let me move this over. Maybe if I move this guy over. So I've got 0.5, let me back up. So it was 2 times, parentheses, 0.5 raised to the 1 divided by 703.5, 1.99803. So if I go back to my, so 1 point, and what was that number? 1.99803. Let me move this up just a little bit. So 1.99803. This is the number of pounds of uranium left after 1 million years. What does that say about uranium? It takes a long time for the uranium to decay. Like I said, it would take 703 million for it to get to half, to get to 1 pound. So after 1 million years, we've still got almost 2 pounds of uranium still there. Okay, let's look at the next one. Oxytocin can be administered intravenously through the blood or intranasally inhaled through the nose. The initial dosage is 25 milligrams. The half-life of each method is shown below. Okay, write an equation that models the amount of oxytocin in the bloodstream after S seconds of injection. Okay, so we're going to just say after S seconds, I'm just going to use the model. The formula is my half-life, Y equal A times 0.5 to the X over H. Okay, so oxytocin, let's just use that to be O. So O, a function of the seconds, so the amount of seconds. So O is my oxytocin in seconds, is going to be, what's the initial dosage? 25 times 0.5 to the S over, what is the half-life? The half-life, well, I've got a couple of things going on here. They said that S is measured in seconds, okay? So I've got to figure out how many seconds. So 3 minutes is equal to 180 seconds. So this is going to be 180, okay? So my half-life is 180 seconds. So the units have to match. So here's my model. So where 25 milligrams, that is my initial value. S represents the time in seconds, and then 180 is the half-life, also measured in seconds, and then this variable O is going to be the amount remaining, okay, in milligrams. How much oxy is left after 2 minutes? Okay, remember my problem here is in seconds. So 2 minutes is equal to 120 seconds. So let's just use our formula. So O, and I'm plugging in 120 here, 120 seconds, is going to be 25 times 0.5 to the 120 divided by 180. So I'll go to my calculator. So 25 times 0.5 raised to the 120 divided by 180. And that is 15.749. So we've got 15.749 0.749 milligrams after, what was that, 2 minutes or 120 seconds. Now, that was in the bloodstream. If it has gone through a nasal inhaler, the half-life is 2.5 hours. Write an equation that models in terms of hours, okay? So the amount of oxy measured in hours is going to be still that initial dosage, 25 milligrams, 0.5. Well, the half-life is 2.5 hours, so it's going to be H over 2.5. Let me back up. It may be confusing here with the H's. Let me just make that a T. It's probably a better thing to do. So O of T, so T over 2.5. So here, this variable T represents time in hours, and 25 is my initial milligram, and then O of T, that's going to be my amount, future amount in milligrams, okay? And my half-life was 2.5 hours. How much oxy remains after 1 hour? So this is going to be substitute the value 1 into this equation. 25.5 to the 1 over 2.5. So we go 25 times 0.5 raised to the 1 divided by 2.5, and that is 18.94. So 18.94. So I get 18.94 milligrams after 1 hour. So what you can see is, in this bloodstream model, after 2 minutes, you have, about 10 milligrams has gone away. And then the nasal, after about 1 hour, you still have quite a bit. You've only lost about 7. So it's held in your body much longer. So it's much faster half-life in the bloodstream. Okay, so let's take a look at the next question. How long? This means I'm solving for my variable, which is my exponent, which is time. Beauty of this from now on is we're no longer using logarithms, we're using our nsolve command. How long will it take the oxy level to reach 5 milligrams in the intravenous model? So I'm saying I want my future answer to be 5 milligrams. So 5 is equal to 25.5, and I think I had what, to the x over 180. So I need to solve this for x. The command on your calculator is quite simple. It's just the nsolve command. So all you have to do is just put in this equation in your calculator and then comma x. It says, go take this equation that I just entered and solve it for x. So if we do that, so I've got nsolve and so I've got 5 equal 25 times 0.5 raised to the x divided by 180, and then comma x. So I'm looking for my comma real quick, comma x, and there we go. So solve that equation for x. X is 185.75. So let's go back and see what that represents. So x is 185.75. This was measured in seconds, okay? So it's going to take 185.75 seconds to reach 5 milligrams, okay? So again, this is just a very specialized form of exponential decay, okay? So when old skeletal remains are found, there's carbon in any living thing. So carbon dating can be used to identify the approximate age of a remain, because carbon decays after a living thing has died, okay? The carbon-14 in the skeleton has a half-life of 5,715 years. An average living person has about 0.803 microcuries of C14 in their remains upon their death. Write an equation that models the amount of C14 based on the half-life of C14, okay? Remember, this is what I'm basing everything on with half-life, 0.5 to the x over h. So if I'm modeling something here with carbon-14, okay, so I can say C of T is equal to, okay, what is the initial value? 0.83, and then 0.5 to the T over, what is it, 5715. So this is the equation. This will model exactly what I want, okay? So it's going to give me the value of C. That is the number of microcuries of C14, okay? 0.83 is the initial value. T is the time measured in years. Okay, and we know that the half-life is 5715 years. How much C14 would be in a skeleton 1,000 years after death? All you have to do is plug in T equal 1,000 into that equation. So C of 1,000 is 0.83 times 0.5 to the 1,000 divided by 5715. And then we go to the calculator. So 0.83 times 0.5 raised to the 1,000 divided by 5715. And I get 0.7352. So I get what was that again? 0.73512, 0.73512 microcuries after 1,000 years, okay? How old would a skeleton be that was discovered with 0.12 microcuries? Okay, how old means I'm solving for time. Time is the exponent, okay? So 0.12, when does the level reach 0.12? So I go back to that same equation, and I'm solving for that exponent t to figure out how much time would it take for it to get to 0.12. And here again, I'm just going to use my nsolve command. So it's nsolve on your calculator. Type in that equation just as you see it. And if you use the variable t, you have to end it with comma t, telling it I need you to solve for the variable t. So nsolve, so N S O L V E, and 0.12 equal 0.83 times 0.5 raised to the t divided by 5715, and then comma t, okay, and no solution found. Let me check this real quick. Okay, so what happened here? In this particular problem, I used nsolve, and if I go back to what we actually did, there was no mistake in what we did. We had, let's go back to 0.12, there we go. No solution found. Okay, this is a problem with the calculator. So this is why we taught you logarithms first on, because your calculator is going through certain methods to approximate this answer, and it's found a situation where it can't solve a problem. So you're probably not going to see one like this on a test, but in this case, we know how to solve this without the calculator, okay? So we know that 0.12, or without that command, is equal to 0.83 times 0.5 to the t divided by 5715. So I need this to be all by itself. So I can write 0.12 divided by 0.83 is equal to 0.5 raised to the t over 5715. Now this gets converted to a logarithm. So this tells me that the log base 0.5 of 0.12 over 0.83 is equal to t divided by 5715. My goal is to solve that for t. To solve that for t, t will be equal to 5715, and is that the right number that I've been typing down? Yeah, 5715. 5715 times the log base 0.5 of 0.12 over 0.83. So I just need my calculator for that approximation. So 5715 times the log base 0.5 of and 0.12 divided by 0.83 equal. And let's back up. I did make a mistake there. It is not the log of 5. It is the log .5. So 15945.3. So let's just round that off, 15,945. So that tells me this skeleton is about 15,945 years old. Okay. So again, in this section, like I said, it's a very specific case of exponential decay. So what it means is every problem, that decay factor is going to be 0.5. So you need to come up with calculator with formulas using based on this half-life model. You can write an exponential model, and then from there you can go ahead and answer the questions. So let's work through the classwork just to make sure that you've got this down. The bomb that dropped in 1945 contained plutonium-239. The half-life of plutonium-239 is 24,000 years. If the bomb contained 14 pounds of plutonium, write a model to show the amount of radioactive substance remaining in Nagasaki. Okay, so the plutonium, the amount of plutonium as a function of time is going to be, it started out at 14, and then it's 0.5 times t divided by the half-life is 24,000. So they wanted us to write something r of t, so let's just change that to an r of t. R represents the amount of plutonium after t years, and t represents the time in years. Okay, how much remains in the year 2000? So in the year 2000, so the year 2000 minus 1945, that's a span of what, 55 years. So it's going to be R of 55 is equal to 14 times 0.5 to the 55 divided by 24,000. So 14 times 0.5 raised to the 55 divided by 24,000, 13.9778. So 13.9778 pounds in 2000. This is why people are so concerned about nuclear weapons, because what, in 55 years, that 14 pounds of plutonium decayed to 13.97. It hangs around forever. Okay, let's look at the next one, something that doesn't hang around forever. You probably have no idea what this is. So cocaine in the bloodstream will be in the bloodstream for less than 2 hours in the half-life. So when mixed with alcohol, cocaethylene is formed, increasing the concentration of cocaine in the blood to more dangerous and often fatal levels, increasing the half-life, or the amount of time the substance is in the body. So the amount of cocaethylene in the bloodstream is modeled by this equation, where C is the amount of cocaethylene in milligrams T hours after consumption. What is the initial consumption? Doesn't take a lot to know. It is 65 milligrams. You can read that straight from the formula. Looking at formula, what is the half-life? The half-life is 7 hours. I can read that straight from the formula. How much coca-ethylene is present after 10 hours? So I need to just substitute the value of 10. So C of 10 is going to be equal to 65 times 0.5 to the 10 divided by 7. And let's figure out what this will be. So that is what, was it 65? Yes, 65. So 65 times 0.5 raised to the 10 divided by 7 is 24.147. So you'll have 24.147 milligrams of the original 65 after 10 hours. How many hours? Okay, I'm solving for the exponent. How many hours until I reach 10 milligrams? So I'm saying I want to end up with 10 milligrams out of my original 65. I got to solve that for T. That's going to be NSOLVE on my calculator. So NSOLVE. So I'm asking for when it reaches 10. Okay, so 10 equal 65 times 0.5 raised to the T divided by 7, and then solve that for T. And that is 18.90. So that tells me it is going to be 18.90 hours to reach 10 milligrams, okay? So that original 65 milligrams stays in your body for 18 hours until you get to 10 milligrams. So it takes a long time to get that out of your system, okay? And that's it for the classwork, and then you've got homework to do from here.